Enthalpy, also known as heat content, is the total energy associated with the materials that react. We use the symbol H for enthalpy.
But teacher, isn't it difficult to measure all the various forms of energy?
Indeed, we cannot measure enthalpy, but we can measure an enthalpy change when heat energy is exchanged with the surroundings, keeping pressure constant.
Oh, that means the enthalpy change of a chemical process is the heat energy that is transferred between system and surroundings at constant pressure.
Nice job, you nailed it. Since the amount of energy released or absorbed is large, we measure the value in kilojoules per mole.
Got it.
We also have mathematical interpretations to determine enthalpy change. The change in enthalpy equals the difference between the enthalpy of products and reactants.
Hang on, we're using the symbol delta here. It is used to measure a change in quantity, right? I've seen this symbol many times in physics.
Yes, definitely. The triangle-shaped symbol is the uppercase Greek letter delta. It measures the change in quantity. For example, delta T means a change in temperature and delta H means a change in enthalpy.
Understood. I also remember that we use an energy level diagram to represent which energy level is occupied by a substance.
Correct. Chemists also call it an enthalpy level diagram. Let me show you how it's made. Let's draw a simple enthalpy level diagram for an endothermic reaction. We label the x-axis as a reaction pathway and y-axis as enthalpy. Then, we label reactants on left and products on the right. During an endothermic reaction, energy is taken in from surroundings. Therefore, the energy of products will be higher than the energy of reactants, having a positive delta H or heat change. The enthalpy change in this reaction is plus 572 kilojoules per mole.
Wow, that's so easy.
It's pretty straightforward once you get the hang of it. Why don't you try an exothermic reaction?
Sure. What reaction do you want me to do?
Try drawing the diagram for the complete combustion of methane. The heat released in this case is 890.3 kilojoules per mole.
Okay, let me give it a shot. For the complete combustion of methane, we know that methane reacts with oxygen to produce carbon dioxide and water. We label the x-axis as a reaction pathway and the y-axis as enthalpy like before. Similarly, we label reactants on the left and products on the right. During an exothermic reaction, energy is given out to surroundings. Therefore, the energy of products will be lower than the energy of reactants, having a negative delta H, or negative heat change. Enthalpy change in this reaction is minus 890.3 kilojoules per mole.
Bravo! But before we move on, we must address the last thing missing here.
Missing? But teacher, I did exactly what you told me.
Yes, the previous two examples are simple enthalpy level diagrams. Actual enthalpy level diagrams for real reactions will never appear that way, as the activation energy must show up on the graph.
Does it sort of activate the reaction as the name suggests?
You're kind of correct. The activation energy is the minimum amount of energy required to start a chemical reaction. It is usually denoted by EA.
Then how do we include the activation energy in our enthalpy level diagrams?
Let me show you. We draw the graph and label the x and y axis as the reaction pathway and enthalpy just like before. Similarly, we label the reactants on the left and products on the right like before. But instead of going straight from reactants to products, we introduce a bump in the graph. We label that bump the activation energy. For an endothermic reaction, the overall energy change is always positive.
Oh, I understand now. Let me try to draw the graph for exothermic reactions, since it's going to be similar as well.
Of course, go ahead.
Like before, we draw the graph and label the x and y axis as the reaction pathway and enthalpy, and we label the reactants and products. Similarly, we introduce a bump in the graph. We label that bump the activation energy. For an exothermic reaction, the overall energy change is always negative.
Want to learn more? We have additional learning resources to offer for Cambridge IGCSE and AS A-level subjects. Register now for free.